Thank you. So as you already introduced, I'm a Senior Vice President of Engineering SingleStore. For the past almost 2 decades, I've been doing databases. Super excited to be here at SingleStore. Our vision effectively is to build a general purpose database that can provide scale, speed, reliability, and unification of real-time applications and operational analyticals in one place, right? So that's the idea of this presentation. I'm going to focus on how to enable your SaaS applications with a cloud-native database. You could build SaaS applications in multiple different ways, but we're going to show how to do that in a cloud-native database in the most efficient way. Right? The agenda is the following. We want to talk a little bit about how the proliferation of modern SaaS applications has been going on, show a little bit about how these architectures have been evolving, somewhat more complex to something more simpler. We're going to show a better way to do this, basically, through SingleStore. I'm going to show a demo. I'm going to show a demo which kind of talks about how to do real-time digital marketing in a cloud-native database. And then finally, I also want to go into the details of how we built such an architecture. It's not easy to do these kinds of promises, right? I'm going to show how it is built so you get an idea of how such a unified system can be built. But before we go there, I want to touch upon how modern SaaS applications are proliferating, right? Imagine for a moment, kind of think about how in the past, when you had these mobile applications or digital experiences of early 2000s, late 90s, et cetera, when the mobile applications have started springing up, even not even mobile applications, any SaaS applications for that matter, right? They were pretty static. They were pretty static when the user had to give, basically it was a one-way direction. There was rendering content, and there was not much of interaction between the user and the system, let alone between the users. Then the social media, the networking sort of started springing up, and everything changed, right? Significantly large number of applications have grown up, and they all require a significant amount of interactions. And the thing that really binds them all together is the real-time nature to it, right? These are a few examples where there's so much of real-time activity going on, right? Whether you're using Google Maps, Uber, any fintech kind of applications, et cetera, they all need that real-time analytics, and thereby you basically see these kinds of pressures, right? There's significant amount of analytical capabilities that are required for these digital experiences, as well as customer experiences which are more operational in nature, right? They want low latency access, and that's sort of a very common theme that you would see across all kinds of applications these days. And what are the interfaces? Well, they come in different forms, right? There's real-time APIs, there are mobile applications, fast applications, dashboards, et cetera. They're all putting significant amount of pressure in making sure that there is a very seamless digital experience. If you kind of look at your own mobile phone and look at all the applications, most every one of those apps are real-time applications, right? They really require that digital interactivity kind of an experience, putting the pressure on both sides, both low latency access as well as real-time analytics. And how do you build such kind of an application? How do you really categorize them, right? Some of the characteristics do come up very clearly here. So these are a few of them. The data keeps growing up, and not just that there's a big data, but there's also an ingestion of data, right? Like there's a significant amount of fast ingestion here, and all of them require low latency, right? The queries are growing quite fast, and they want results to come in really fast, right? So they want both the CRUD nature of the request to happen in single-digit millisecond kind of latency, as well as like analytical queries that need to happen really fast. And then, of course, as the applications are growing, there's a significant amount of concurrency, right? When you think about an Uber app, for instance, there is a game, let's say, and as soon as a game is finished, a significantly large spike of users are demanding some ride apps, right? So they're going to use that, and they want drivers to be sort of like, in the neighborhood. You're putting in a lot of pressure on these systems. So when you combine these factors, there's a lot of big data, fast ingestion, you want low latency of queries, a significant amount of high concurrency, and you sort of define the data-intensive applications with these characteristics. If your application has a few or all of these characteristics, then you're dealing with a data-intensive application, right? And that's sort of what we have been serving as SingleStore. And before I go into further details, I just want to point out that These are some of the Fortune 500 customers, not just Fortune 500. In fact, there are a lot of disruptors and startups, et cetera, who rely on single store to build these data-intensive applications to grow their business. A lot of these use cases are live, and I encourage you to go look at them. And I want to touch a little bit about how the architecture has evolved to serve these kinds of applications and show about how single store kind of simplifies it before we go into further details, right? So here is sort of an old way of doing it. You start with the relational database. Here I use Postgres. It could be anything really, doesn't matter. It could be MySQL, it could be Oracle SQL Server, whatnot, any vanilla relational database, right? You start with this, you have some ingestion of the data coming in, and you can write your applications on top of it. Maybe you have some operational data coming in. This is some real-time CRUD kind of data coming in. This is fine. So far, it's all good. You have a single node system, perhaps, single node database, perhaps, data coming in, applications taking care of their own requirements. This is sort of the old way to begin with. Then the complexity starts creeping in, right? You may have a third-party applications which require unstructured data. Well, maybe then you put Mongo on top of it, right? Now your application is already complicated because it has to deal with two databases. And the databases themselves need to be in sync. So you have to do some streaming out, streaming in between the systems so that there is consistency of data, right? Well, you're not happy with the speed, then you put Redis or cache kind of a system on top of it, right? And then you kind of start complicating the application paradigm even further, right? And then maybe you want aggregation analytics that are much more advanced than what the existing systems offer, maybe full text search, et cetera. Well, then you put Elasticsearch. What about data warehouse? What about streaming? You keep adding these systems. And then finally, I also want to point out that you may want to do some operationalization of your models. You could sample the data out through Spark. Maybe you're using Databricks here. Then doing your AI/ML outside. You could do the modeling outside by sampling the data in and then operationalize it back in the system. And a lot of systems do that. Now, when you kind of put this together, it may seem like I'm exaggerating a little bit, but trust me, it's not at all exaggeration. This happens all the time. It may be the case that a lot of these companies don't have all of these options, but they do have a good number of these sort of different databases working through one application. This happens a lot more frequently than what you could imagine. We have seen many customers doing this. And what ends up with this thing is that you have a significant complexity and cost. You have a lot of data movement, and of course, when you have data movements, you have latencies. And then that leads to multiple points of failures. And these are common problems that happens whenever you have an architectural creep, right? And the application is really under a lot of pressure. There's a significant amount of cost for the engineers to go maintain this. And the experiences, the business experiences are not that great either, because you now have to deal with so much of latency of data, movement of data. It's just correctness of data is harder, and all that stuff, right? What we offer here is much simpler solution. To start with, take single store. We still recommend that you basically train the data out, and use Databricks as Spark here. Go to AI/ML modeling. We're really good at operationalizing that model. You can bring it back, and we can operationalize it really effectively, given the characteristics of our system. Once you have that, let's say you have batch data, you have operational data. You can start putting all this data. You may even have a third-party data. Let's say you have JSON data that you want to bring into the system, no problem, right? You can just bring them all into one system because the system is designed to handle multi-model, right? It's designed to handle both operational and batch. Now, let's say you have some streaming data coming in. We have a feature called Pipeline that is incredibly suitable for doing that kind of streaming in a significant amount of data into the system. If you can handle all that, you don't need another database for this. And then your application is happy. You don't even need Redis. We have actually proven that we could do single-digit millisecond latency, given the architecture. And I'll go into the architecture in a bit to back up these claims, making big claims here, right? So definitely going to back it up here. The claim here is that your application is going to be much simpler because it's really dealing with one system instead of multiple systems. So you can do away with that database creep here and simplify it. And it's not just about the simplicity, it's also about the speed of serving insights. Because you only have one system. The data doesn't need to move around, right? You can do transaction analytics, so the cost is lower, the time to insights is minimized, so it's all good, right? I mean, here are some live examples. There are many of our customers who have taken all these systems, simplified it, because they could do all those things in one place with single store, right? Let's take, for instance, Sony, right? They have been working on Postgres, Elastic Cache, and DynamoDB. When they look at single store, we can give that single-digit millisecond latency, distributed nature of key-value stores of DynamoDB. We are relational foundations. They don't need Postgres for that. And we can do aggregations, geospatial queries, and whatnot. We also have a full-text support. So you sort of compress all these pieces into one place. Let's take Fathom. Fathom has, they took away their MySQL, Redis, and DynamoDB pieces all in single store. And there are many such cases. They're all on our website. Here are some of the quotes. Uber, for instance, has been our long-running customer. Uber basically uses us. Whenever you go to your Uber app and try to hail a ride, basically it's making requests into a single store to figure out the best way to serve the customer needs, right? And this has been a long-running customer. They successfully use us to do the real-time analytics and operational requirements, right? Fathom, this is an amazing quote. In March 21, we moved all our analytics data to the database of our dreams, right? And this happens a lot. We see this quite a lot with our customers. Now, okay, so this is all great. Let's get into some details to see how this happens, right? So before I go into the details, I want to show a demo. I want to show you how you could do a real-time digital marketing in single store, right? There is a GitHub link here. This link has all the code. You could take this code, look at it. There is some synthetic analysis, synthetic sort of data generation going on. So if you want to change it, challenge our claims, et cetera, welcome to you to do that. You can create a free trial cluster and run this demo yourself, make changes on the code yourself, all free of cost. You can do it right after this demo. Let me show you how this works. So here's the site where you could go and play with this. This is a single page which kind of walks you through the demo. It talks about what this demo is about. So let me give you a little bit of a context about what this is trying to do. We're trying to simulate here real-time digital marketing. What is real-time digital marketing? When you think about how the digital marketing has evolved, it basically had two different entities. There's customers and there is a company. There are multiple customers, lots of companies. Customers have a few things going on. They have a purchase history. They may have, let's say you're a customer, the customer is purchasing a lot of shoes, or maybe the customer is purchasing a lot of coffees, let's say, right? They went to a certain grocery store and they're purchasing a different, there's a purchase history there. And the customer is moving around, so there's a location aspect of the customer. Where is the customer, right? That's important because you don't want to market to a customer who is not in the right location, right? I'm gonna head back to Seattle in the evening today. If I get an offer from a company here for San Francisco in the evening today, that's useless because I'm going to be in Seattle today evening, right? So sort of you need to offer the right campaigns for the customers based on what their preferences are and what their locations are, right? So there's the aspect of the customers whose choices, purchasing choices, as well as locations. On the other hand, the companies, obviously the companies are generating offers. They're generating these offers to sort of lure the customers in purchasing them. So companies are generating the offers on the other hand, right? The challenge is to segment these customers based on their purchase history and map the offers at the right location, the right time, right? And this needs to happen in real time. The example that I just said, if I get an offer for San Francisco when I'm in Seattle, it's useless, right? And it's just, even if it is 1 hour off, it's kind of pointless, right? And if they're taking my purchase history from several days ago, that also may be irrelevant, which means that we need a system that kind of takes all these pieces in real time and build these matching algorithms. That's not that easy. You could solve it in multiple different ways. I'm not saying that this is the only solution. But the point is, when you're solving this solution, you want to focus on lower TCO, simplified architecture, and significantly lower time to insights. Once again, you could solve this in multiple different ways, but you have to really focus on the choices. And this is a proper example of a data-intensive application, or so to speak, real-time analytical application. So here, I basically have the setup already in place. I have just created the schema for it. I didn't do anything else. The schema, this demo page kind of really walks you through. You just have to put your cluster information, your username, password, et cetera. And this is just, you could go create one yourself. This is the schema. Let's just look at it. Here is a SQL for offers table. It just talks about, hey, what is the offer ID, who's the customer, whether it is enabled or not, et cetera. This is purchases information. This is about the customer. So all the information about the customer, the attributes that I just talked about, the customer, the attributes about the company and their offers, they're all just here. You could look at it. You could change them yourself if you want. But that's all set up. So I've already finished that setup, right? And I have in my portal the database here, right? This is the database MarTech. This is just what we've created. Now let's go do the actual live demo. So step one, I'm going to ingest data. So ingesting data is effectively, it is simulating the nature of building in pipelines. So it kind of simulates the location history, the location tracking, the purchase history of the customers. They're coming in, and we are just sort of simulating based on some data that we have in S3. Think of it as the real-time streaming that's coming in, right? We use a single store pipelines. In fact, you can reason over what the pipeline is. Just piping in the pipeline from the corresponding location here. And the data is coming in live, right? This is live, and this is sort of like you can reason over this. This is 1.3 million locations and so on and so forth about the requests and purchases are going on, right? We're just sort of simulating this data. So this data is coming in live, and we're crunching that data in real time. Now, on the other hand, let's go to offers. This is what the companies are trying to do, right? The companies are trying to place offers, and each offer has certain information, maximum bid price, activation, segments, et cetera, right? We're going to use a small polygon of New York City. We could go, of course, very broad, but for this demo, we're choosing just one small section. In that small zone of New York City, we're going to show how these offers are being mapped to the customer. Right? So let's just load offers. Again, simulation, right? So this is a place in New York, which is pointing out these are the number of offers that are being generated. So while this is happening, so there's live data coming in, offers are being generated. The first thing that we need to do as a system is to segment these customers. We need to point these customers to, this customer bought a coffee in the last day, or they visited a grocery store. Based on such kind of information, we have to segment. So we're running some heuristics here, and we're just matching the subscribers to segments. And this keeps running in the background. Here I just showed, we can keep doing it, right? And it's super fast. It's taking, 228 milliseconds to segment these many rows. That's huge, right? And now final step is to match them, right? So you have the location, purchase history coming in. You segmented them already. You have the offers being loaded from the company. Just match them, right? So we're doing the notifications now. As you can see here, these notifications are happening all the time. Every time you do some notifications, you can zoom in and all that. So you can put it all together. You can watch this in a live dashboard. This is sort of showing you what's happening across the board. These are the number of offers. This is the amount of time it takes to do the matching, time it takes to do the segmentation. This is all live. You can play with this code. This is an amazing analytics dashboard which shows you synthetic data, of course. As I said, the code is all available. You could play with it. This kind of drives home the point as to how challenging this problem is and how single store simplifies it, right? You could increase the amount of load. You could play with a different cluster size. We welcome you to do it. In fact, we'd love for you to send us some feedback about this. I made significantly large claims, and here is a proof in action, right? We've taken a massive amount of data in real time, generating insights real time, and there are two aspects here. There's one aspect which is insert the data in an operational latency, which is single-digit milliseconds, and read point lookups, et cetera, in operational latencies, right? You may want to know the history of a person. You may want to find out or update the location of the person. And this should not happen in a sort of a data warehouse-style latency. That won't work, right? Because you want the latency of the location adjustments and the purchase history to be happening real time. On the other hand, you're running significant amount of analytics. You're matching these offers. You're doing significant amount of segmentation, et cetera. That also need to happen in real time. And this is a problem that most of the SaaS applications need to encounter. And what you end up doing is significant amount of data engineering work, pipelines. You may be doing some data warehousing, some operational workloads, some Redis, et cetera. We don't need it in single store. Once again, a big claim. Let's see how we do that, right? So let me go back to the slides and talk about things under the hood, right? Now, how did we end up building it, right? So this is my last section here. I want to touch upon the architecture of the system, right? Before I go further into this, I want to point out that we've just published a Sigmod paper. There's an amazing presentation here. There's a paper in Sigmod that kind of goes into a lot more details than what I'm touching upon here. I encourage you to take a look at that. So to start with, this is a horizontally scaled shared nothing architecture. It's a relational database. It's a relational foundation database. It's multimodal, but it's mostly relational foundations, right? It is horizontally scaled, distributed, shared nothing architecture. There are two kinds of nodes here. There's an aggregator node and leaf nodes. Aggregators are basically taking in the queries, planning the queries, and executing sort of the inter-partition queries. Leaves are basically where the partitions are, and the replicas could be. And they're responsible for storing the data and doing the intra-partition queries. Now, obviously, given that it's a shared nothing architecture, you have partitions and configurable number of replicas. Here, for examples, I'm just showing 2 replicas. You can have more. And there's a primary, secondaries, multiple secondaries, et cetera. Given this architecture, we can scale out as much as the data and the throughput demands. And this aggregation capabilities essentially satisfy the challenges of a distributed QP, right? That's kind of what I'm showing here. Nothing unusual so far. And we rely on replication, of course. We want to make sure that the changes are logged and replicated for availability and durability, just like how you'd expect in a distributed database. Again, nothing unusual. One interesting thing is that the transaction is committed only after a configurable number of replicas have locally committed it. Now, there are 2 kinds, durable commit and volatile commit. Our default is to do volatile commit, which is basically keep it in memory. Once everyone gets that, you sort of acknowledge back to the primary, which then acknowledges to the user when the request is done. This is interesting because with this approach, you don't have to touch the blob or disk in the commit path. Basically, volatile committing in memory and going fast. It makes it really fast. The downside is that, obviously, if you crash all the replicas, then that is lost. So you could configure it if you want to do durable commit. But the trade-off is nice because you could have these replicas in different availability zones and whatnot, right? That's also not all that unique. Many of the distributed database systems do it. Where it starts to change is when you look at the individual partitions and how we sort of lay out the data. If you kind of zoom into a partition, this is how a table's data looks like, right? In memory, we keep the data in row format in a skip list index, right? This is sort of helpful for operational workloads, right? You could do CRUD APIs, so you could do simple sort of insert, delete, updates, et cetera, really fast because the data is in memory, and sort of you could do that. That's how we began as a company. In fact, we're offering scaled out in-memory OLTP system with skip list indexing. Makes it really fast. Obviously, it's harder given that you might have a lot more data than the memory footprint could offer. At that point, we start moving the data into the disk, right? When we start moving the data into the disk, we actually don't store the data in the same format. We store it in columnar format, right? Now we went from row-oriented to the columnar-oriented. When you start, and then we have some metadata in the memory, which sort of helps us do the mutations, effectively some bitmap manipulations to tell us how to adjust the immutable files. Because once the file is packed, a segment is packed on the data, given it's a columnar, it's immutable, right? So we have some metadata that kind of helps us make additions. So for instance, if you want to do an update, you'd have to set a delete bitmap and insert a new row in memory. And then after that, the entire system basically flows through as a log structure merge tree. It's an LSM tree, which essentially means that the data will be put in locally sorted segments, and there's a background merging that happens, which is creating a more sort of globally sorted files, or more than the locally sorted files. It basically constantly keeps merging, and that creates another level, right? So the change here is that we are in memory row store. On disk, we have a columnar format, right? Well, that's something new, right? That's something that's not all that common. So there's change number 1 here, right? And then the other thing that I want to point out is that everything here that I pointed here is a log structure merge tree, right? And then, of course, we've done a massive amount of improvements in our query processing. Query processing is super advanced. It is probably one of the rare engines that can do both TPCH, DS, as well as TPCC workloads, and I'll talk a little bit about our benchmarks in a bit. And there are lots of papers here, research papers that we've published, Sigmod, VLDB, et cetera. I encourage you to go take a look at them. We push down these queries to the leaves where the partitions reside, of course, and we have a fascinating distributed QP as well. The queries are compiled to LLVM. We take advantage of the hardware primitives to do vectorized execution and all the goodness that you would imagine here. But the beauty of this system is that it kind of combines that row-oriented in memory with the columnar format on disk, right? So that's right there. There's some change here. Finally, when you kind of put these pieces together, you have these aggregators, and you have the leaves where the data is stored, and that's kind of where the log tail is, the data file caches are, et cetera. And then there's a blob storage here. The way data moves from these leaves to the blob storage is interesting. It happens in an asynchronous fashion. We've introduced blob storage in our sort of the latest phase of our evolution. We've talked so far about in-memory skip list and on-disk columnar format. Now there is this third tier with the blob storage, right? We move this data asynchronously. Now it kind of has lots of advantages and some challenges when you have this kind of an architecture. Advantages are the following, right? Well, when you have that seamless sort of bottomless storage in blob storage, it means that you really don't have to worry about the disk pressure. If you're running out of a disk, you could just keep moving into the blob storage and delete them from the disk, right? When you delete them from the disk, you can keep taking in more, of course. The challenge is how do you bring it back? And we'll get to that in a minute. But this kind of gives you that sense of that bottomless nature, the tiering of storage effectively. It also gives an advantage where we have entire data in blob storage, which means that we can build solutions like PITR very effectively. We could also add read replicas on top of this blob storage very efficiently. All the data is here. Just add more replicas. In fact, we have a concept called workspace that's sort of built on top of this, right? And then given that this nature of asynchronous moving and tiering the data from disk to the blob storage, you can think of disk as a sort of a write-ahead cache, effectively, right? When the query demands the data to be pulled back, then it needs to sort of maintain a replacement policy and be very smart about that. We handle that. Now, the challenge is that if you rely on blob storage as sort of your final destination or as the actual sort of durable storage, then there is a risk. If all the leaves crash, then the log tail, the amount of data in that tail could be lost as well. Once again, you could keep these replicas in availability zones to minimize that. It's a good trade-off, effectively, is what I'm trying to say, right? So with this combination in this layering of sort of memory row storage, columnar on disk, and this tiering into blob storage, and different formats with LSM, and again, significant improvements that we have made in our query, we have some really fascinating results here. But before I close, I want to touch one more topic about the universal storage. This is sort of what we've patented this, we've worked on this for quite some time. The idea is that you have these row stores which are really good for seek performance, CRUD, and operational latency kind of operations. And then columnar storage is really good for fast scans, aggregations. How do you basically preserve the best of both? That's the whole challenge, right? We have done some amazing work to create efficient secondary indexing on top of this combined sort of storage, which we call as universal storage, effectively. And it has some really great properties. It can seek to, on top of the column store encodings, you can even do row-level locking, et cetera. And here is a quick example of this, right? When you think about segments in a columnar format, you have the data, of course, in compressed. So let's say you have these two index column, and there's foo, there's bar, and some other data, et cetera. They're all compressed. Logically, we're just showing it uncompressed, but they're all compressed in their own chunks. You typically see an inverted index on top of each segment that kind of points to where the values are. Inverted index is just saying that, hey, foo is in these locations. Bar is in these locations, right? It just helps you get to the exact offset within that segment, right? It helps you sort of avoid the unnecessary seeking within that segment. So that's very helpful. It's sort of like an index in terms of getting to the segment. But there's another problem here with these compressed column store files, which is, well, you got tons of segments. If you want to go to get me all all locations of a value across segments, not just one segment. It's fine if your query goes to one segment and wants to find the value, it's great. The inverted index will help. But how do you get across all the segments the positions of a value? Right there, we build another global index. This is hashed. So we take, let's say, foo is hashed to 0x24. It kind of tells you all the locations across all the segments. So it just gives you a pointer of, it's there in segment 1 at this offset, it's there in segment 2 at this offset, and so on and so forth. So with these additional pointers, you sort of can go across all the corresponding segments, and once you get into the segment, use the inverted index and get to the exact offset. This kind of makes it really fast. All you need is log and hash tables to kind of go through all the segments to get the results that you want. So this is really just a flavor of some of the innovations that we've done. This kind of helps you preserve the operational latency for transactional applications without losing the scan performance that you typically expect from a data warehouse, perhaps, right? Like, in terms of columnar queries. And here's some really quick study on the benchmarks. GigaOM, a third-party independent vendor, basically did these studies, and the study found some really amazing results here. On TCO, if you are sort of using Snowflake and MySQL, the reason why you have to use these two stacks compared to single store is what I've already explained. You need the transactional nature as well as operational nature, so you sort of do this combination of systems, and you see the kind of savings when you compare it with single store. Redshift, PostgreSQL. Then on TPC Edge, we found out this is just pure benchmark studies that we've done. So super fast, really cheaper, amazingly simpler kind of a developer experience. And that's kind of really the idea and how we've achieved this SaaS applications, supercharging your SaaS application, so to speak. Yeah, that's kind of really it. I'm going to open up for Q&A.
Thank you so much, Harish. At this time, if anybody has any questions, I'll run over to you and you can ask Harish.
Yeah.
Anybody? OK, cool. I have a couple questions myself. Which cloud providers is single store available for?
We are available in all the cloud providers, so all the major cloud providers. And we are cloud native, so if somebody wants to host the system themselves anywhere, you could do that as well. So we have all the flavors, effectively.
Very cool, very cool. And then as far as the replicas go, I know you mentioned that you can replicate across availability zones, but can you also do across regions as well?
So that's coming up pretty soon.
OK, very cool.
So we are adding GeoDR pretty soon, so we do have availability zones, but yeah, it's coming up pretty soon.
Awesome. And then one last question. This one's a little bit harder. I'm a member of a DevOps team. I'm ripping my hair out because I'm going through the problem of managing multiple data stores. How do I migrate my data into a single store? Do you have any scripts or anything that could help me?
Yeah, so we've spent a lot of energy in solving that problem. We have a feature called pipelines. Pipelines are effectively really one of the most amazing ways, streamlined ways to ingest the data in. It is designed to bring the data in parallel across all partitions in the most efficient way. And then on top of it, we also have a lot of CDC in vendors that we could sort of partner with. So if you want to have any kind of translations, et cetera, before we bring it in, we could do that. So we have some partners that we work with for that as well.
OK, and then one last question here. I've tried your demo. I'm really excited. Who do I reach out to get started with my enterprise?
Yeah, so you could just tweet me at Shirish Tota, one word. Just single store DB is another tweet handle that you could reach out to. Yeah, I mean, those are probably the easiest ways.
Very cool, very cool. Well, thank you so much, Harish. If you're joining us virtually, please give the session a review. Go read the research papers, Sigmod and VLDB. And then if you have any other questions, feel free to catch Harish after this session. Thank you all for joining our session today. Cheers.